Year 9, solving equations using a numerical method which we call trial and improvement. In today's lesson, we will start by recapping some work on solving equations using algebraic techniques, and then we will move on to looking at equations which we cannot solve using these simple algebraic techniques. How do we go about solving them? We have to use other processes, including something which we're going to introduce, which is called trial and improvement. So we're going to start off by looking at a little starter activity where we have to solve some equations using algebraic methods. Use this as a warm-up, have a go at the 7 equations, use algebraic techniques to solve each of these. So here is the first set of equations that you're going to have a go at solving. Pause the video, have a look at each equation, work it through, and then unpause the video and check your answers. So, question 1, we're going to start by expanding the brackets. So we have 4x plus 12 minus 2 plus 4x, careful with the minus 2 multiplied by the minus 2x there, which equals 9. Let's collect our like terms. So we have 8x and then we have plus 10 equals 9. Then we're going to subtract 10 from both sides. So 8x is equal to negative 1. And then divide by 8, so x is equal to negative 1/8. And we're done. Question 2, we're going to multiply both sides by 2. So that gives me x plus 3 equals 10x. Then let's subtract x, so 3 is equal to 9x. And then divide by 9, so x is equal to 3 over 9, which of course simplifies to 1/3. And our last example, there are different ways of going about this. I'm going to add 4 to both sides, first of all, which simplifies working a lot because we then have x plus 1 over 3 equals x plus 4. Then multiply by 3, x plus 1 equals 3 bracket x plus 4. I've unfortunately rather run out of space here. Make sure you're working down the page as you should be. Expand the bracket on the right hand side, so we have x plus 1 equals 3x plus 12. Let's subtract x from both sides. 1 equals 2x plus 12. Subtract 12, negative 11 equals 2x, and then divide by 2, so x is equal to negative 11 over 2. So we've got another 3 equations coming up. Have a go at each of these, pause the video, try the equation, and then come back and check your answers. So let's see how you got on here. Question 4, straight away I'm going to multiply both sides by x minus 2. So that gives me x plus 5 equals 4 bracket x minus 2. Expand the bracket on the right hand side, 4x minus 8. And then let's collect like terms on opposite sides. So I want to subtract x from both sides. So 5 equals 3x minus 8. Add 8 to both sides. So 13 equals 3x. And then divide by 3. X is equal to 13 over 3. Question 5. Now I'm going to multiply by 3. It's not the only way of starting this off. We must, however, remember to multiply all 3 parts of this by 3. So we get 15, subtract x equals 3x, add x, 15 equals 4x, and divide by 4, 15 over 4 equals x, or x equals 15 over 4. Now, the last one, question number 6. Lots of different ways of approaching this. I'm going to subtract by 3 on both sides first of all. So 4 over x plus 2 equals 8 subtract 3, which is 5. Multiply by this divisor here of x plus 2, which gives me 4 equals 5 bracket x plus 2. And again, it's just not quite enough space at the bottom of the page here, so we'll move over here. 4 equals 5x plus 10, expanding the bracket. Subtract 10, so we get negative 6 equals 5x, and divide by 5, so that gives us x equals negative 6 over 5. And there's our final answer. Now, in all 6 of these examples, We solved the equations algebraically. We used algebraic techniques. We expanded brackets, we collected like terms, we balanced both sides of an equation. Now, not all equations can be solved algebraically. And there are some equations which we can solve algebraically, but at the moment, at year 9 level, we do not necessarily cover those skills. So there are equations for which we have to use other approaches other than algebraic ones. We have to use a numerical approach instead. And that's what we're going to look at in today's lesson. We're going to look at equations which at the moment you do not know how to solve using algebra, and we're going to apply an alternative approach called trial and improvement to solve these equations. So what about equations that we cannot solve using these techniques? Let's look at an example. So the example we're going to look at is x cubed plus 4x equals 10. So this is an example of a cubic equation. The highest power of x is a cube, so it's a cubic equation. And our aim is to find x correct to one decimal place. How do we go about doing this? Well, you have seen a process previously called trial and improvement. We're going to use that. We can't solve this equation very easily algebraically, so we're going to need to look at another way of doing it, and a numerical method like trial and improvement is a good way of doing this. So let's see what we remember from trial and improvement. So you may remember that the process is very systematic and we need to set up a clear table. I'm going to choose a value of x, and I'm going to input it into the left-hand side of the equation here, and that's going to allow me to calculate a value of x cubed plus 4x. And I want to see how close can I get to the answer, which is supposed to be 10, sort of like a target value. And I'm going to comment on whether I'm too high or too low as I input values. So the first number that I'm going to input is 1. So I'm going to input 1 into the left-hand side of the equation here. So effectively I'm calculating 1 cubed plus 4 multiplied by 1. You can do that in your head or you can do that on a calculator. Either way, we get a value of 5. Now, how does 5 compare to our target of 10? Well, it's too low. So I'm actually going to write down too low or low here. So that means my x value of choice was a little bit too low. So I need to choose a larger x value. So let's be logical here. There's no point going into multiple decimal places until we've checked the next integer value up. So we're going to check a value of 2. So this time I'm calculating 2 cubed plus 4 multiplied by 2, and that gives me a value of 16, which is obviously larger than 10. So that value is too high. Now, what does this tell me? Well, it tells me that because 1 gives me a value of 5 and 2 gives me a value of 16, in between 1 and 2, there has to be a number that gives me a value of 10. So the answer has got to be, the value of x I'm looking for has got to be a number between 1 and 2. So my next logical choice would be 1.5. We're going to continue this on the next page. So here's the information that we have so far, and what I'm now going to do is input the value of 1.5 into my calculator, substituting in x equals 1.5 into x cubed plus 4x. Now this gives me a value of 9.375, which is too low still. So that means my answer has got to be somewhere in between 1.5 and 2, because 1.5 gives me a value that's too low, but 2 gives me a value that's too high. So where next? Well, let's be logical. Again, don't leap around. Go to the next value up, which is 1.6. Now, substituting in 1.6 gives me an output of 10.496, which is a little bit too high. So what does that now tell me? That now tells me my answer is in between 1.5 and 1.6. But remember, we were trying to find the value of x correct to 1 decimal place, which means we need to give our answer for x to 1 decimal place. So our answer is either going to be a number that rounds to 1.5 or 1.6. Remember, we're not finding the exact value of x. It's very difficult to do that. We'd have to carry on the trial and improvement process for a long, long time. And even then, we could still carry on going because the answer could be some kind of surd value, some sort of irrational number that's infinite. But what we know is that the answer is going to round either to 1.5 or 1.6. Now, it's really crucial at this point here that we don't just look at the values 9.375 and 10.496 over here and choose whichever x value gives us a number that's closer to 10. That's not the way to do this. The way to do this is to choose a value that's in between 1.5 and 1.6 and test that value. So the value I'm going to choose is 1.55, exactly halfway between. Now, if we substitute that into x cubed plus 4x, let's see what we get. Well, we get an answer of 9.9238. ... Now, what can we say about that? Well, that's just underneath 10, so it's still too low. So, what does this actually tell us? Well, imagine a number line. Now, on my number line, I'm going to place some values. I'm going to place 1.5, 1.6, and in between them, I'm going to place 1.55. Now, we know that 1.5 gave us a value that was too low, so it's going to go underneath like that. 1.6 gave us an answer that was too high, so I'm going to place it above the line like this. Now, 1.55 also gave us a value that was too low, so I'm going to place that underneath the line like that. Now, if I join these up, we'd get something that looks like that. So because the crossover occurs in this gap here between 1.55 and 1.6, that means the true answer, the actual exact value of x, is a number that lies between 1.55 and 1.6, which means that the true answer for x will round to 1.6 to 1 decimal place. So again, think about the fact that because 1.5 is low, and 1.55 is also low, we don't get the changeover between 1.5 and 1.55. Whereas the value for 1.55 gives us an output that is too low, it's 9.375. The value for 1.6 gives us an output which is 10.496, which is too high. So in between 1.55 and 1.6, the actual answer that gives us a dead-on value of 10 must be over here, somewhere between them, which means it's a number that will round to 1.6 to 1 decimal place, because all numbers in this gap here between 1.55 and 1.6 will always round to 1.6 if you round them to 1 decimal place. So we have found a value of x that satisfies this equation here correct to 1 decimal place, and that value is x equals 1.6. So we're now going to have a look at a second example. Have a look at the equation. We are going to find a root, which is another way of saying answer or value of x, that satisfies the equation x cubed plus 3x equals 32. It's another cubic equation, and we are working correct to 2 decimal places. Let's have a look at our table. So it's all set up for us. We want one column to represent x, one column to represent the value of x cubed plus 3x for that value of x, and then we want a third column to make a comment on whether our output is too low or too high when we compare it to our target here of 32. So let's choose a value of x to begin. So my first value of x, often quite sensible to choose a value of 1, especially if the output isn't that high. Now, if I substitute in x is 1 into 1 cubed plus 3 times 1, I get an output of 4, which is obviously too low compared to 32. Let's substitute in x equals 2. This gives me an output of 14. which is again too low. So I haven't found a gap that contains my actual answer here. Let's try x equals 3. This gives me an output of 36, which is too high. Now, that means that my answer, my true answer, has got to lie somewhere in between 2 and 3. So my ultimate value of x will be 2 point something something, correct to 2 decimal places, but of course we have to investigate a little bit further. So it makes perfect sense for us to try 2.5. We shouldn't really go into the second decimal place until we've found which two numbers the answer lies between to 1 decimal place. So let's input 2.5 as our next value and see what we get. So we're working out 2.5 cubed plus 3 times 2.5, and this gives me 23.125. So that's a little bit too low. So can you see how we're narrowing down the gap in which our root lies? Originally, we knew that the root was somewhere in between 2 and 3. 2 was a little bit low, 3 was a little bit high, somewhere in between them, there's the exact answer. What we've now found out is that we can narrow the gap to 2.5 to 3. 2.5 is a little bit low, 3 is a little bit high, so in between them, there's the exact answer. So we now know the answer lives somewhere in between 2.5 and 3. So I'm going to very sensibly look at the next value up, which is 2.6. Now this gives me 25.376, which is too low. Now this tells me that the answer has got to be somewhere in between 2.6 and 3 now. So I've got it down to the gap between 2.6 and 3. Let's keep going. So 2.7 is my next value to try. So that gives me 27.783, which is too low. So we're now looking at the gap between 2.7 and 3, getting smaller. So 2.8 is the next option, and that gives me a value of 30.352, again, too low. So we have to go for 2.9. Now, what does 2.9 give us? 2.9 gives us 33.089, which is too high. It's higher than 32. So this is interesting because what we've done is we've narrowed the gap to between 2.8 and 2.9. So 2.8 was a little bit too low, 2.9 was a little bit too high. So let's investigate 2.85 and see what we get. So 2.85 gives me 31.699 ... which is just a little bit too low. Now that tells me that the answer lies in between 2.85, which is too low, and 2.9, which is a little bit too high. So if I were rounding the answer to 1 decimal place, I can now say that the answer has got to be 2.9 to 1 decimal place because it's a number that lies in between 2.85 and 2.9. But remember the question said we had to find the answer correct to 2 decimal places, which means we need to carry on going. So I know that 2.85 gave me a value that was a bit too low. Why don't we try 2.86? 2.86 gives me 31.973 ... which is again slightly too low. So on to 2.87. And aha, we have 32.249 ... which is too high. So let me draw out my number line over here. Imagine I've zoomed right in on this. So 2.86 and 2.87. Now, 2.86 was a bit too low, 2.87 was a little bit too high. So the answer lies in between 2.86 and 2.87, and it's going to round to 2 decimal places to either 2.86 or 2.87, but which? How do I know? I choose a value in between them, and the value to pick is 2.865, exactly halfway between them. So 2.865. If we input that into our calculator, gives us 32.111, which is just a little bit too high. So that would be up there. So that means the changeover between low and high occurs here. So have a look at this. You can see if I join up these crosses like that, then the answer must be somewhere in between 2.86 and 2.865, which means when you round that number, it's going to round down to 2.86. So our answer, correct to 2 decimal places, is 2.86. Now, notice how systematically we did this, really carefully. We started by exploring the integers here before we moved into the first decimal place, and we explored the first decimal place until we realised that the number was in between 2.8 and 2.9, and then we moved into the second decimal place. If you start leaping around from one number to another number without doing this systematically, there is a strong danger that you will miss something and your work is just not going to have the logic it needs. So let's have a look at another example. So the volume of this cuboid is 5,000 centimetres cubed. Find the value of x correct to 1 decimal place. So where's the equation here? Well, we've got to set it up ourselves. So what do we know about volume of a cuboid? Well, it's very easy to work out from the information we've got. We know that x multiplied by x multiplied by x plus 4 must give us the volume, length multiplied by width multiplied by depth, and that volume must be equal to 5,000 centimetres cubed. So what can we say? That's x squared x plus 4 equals 5,000, and here's our equation that we're going to solve. Now, if you want to, you can expand the brackets on the left-hand side of this. We don't have to, we could actually leave it as it is, but if you wanted to, that would then give us x cubed plus 4x squared equals 5,000. And that's the equation we're going to solve using trial and improvement. And we're going to use trial and improvement to find a value of x that satisfies this equation correct to 1 decimal place. So you may decide that you want to try this yourself, in which case pause the video, make sure you set out your working very clearly and then come back and check your answer, or you may want to work through this with the video. Either way, make sure you set out your working very, very clearly. Now, we're going to choose a value of x to start with. Now, 1 is not necessarily a very sensible value to choose here because it's so small, and actually if you input 1 you get an output of 5, which is really very small compared to our target, which is 5,000. So I'm going to choose a value of x equals 10, and I'm going to substitute that in and see what I get. Well, it's 1,400, which is still too low. And because it's still quite small compared to 5,000, I'm going to jump up a little bit and choose 15. So that gives me 4,275, which is still too low. Let's try 16 and see what we get for that. Well, 16 gives me 5,120, which is too high. So what do we know? Well, look at the changeover between too high and too low. The number must be somewhere between 15 and 16. So we need to try 15.5, see where that takes us. Well, that gives us an output of 4,684.875, a little bit too low. So that means the answer has got to be between 16 and 15.5. So we need to try 15.6. Being methodical, working through this carefully. 4,769.856, which is too low. So 15.7 is our next choice. And this gives us a value of 4,855.853. Still a little bit too low, so slowly creeping up, 15.8. What does that give us? That gives us 4,942.872. Still a little bit too low, so 15.9 is our next option, and that gives us 5,030.919, so just a little bit too high. So what does that tell us? Well, the answer has got to be somewhere in between 15.8 and 15.9. So if we were to draw this on a number line, which I'll just illustrate down here, 15.8, 15.9, hopefully you can all see 15.8 gives us something that's too low, 15.9 something that's too high. So is the answer going to round down to 15.8 or up to 15.9? Well, we don't know until we check a value that's in between. So we're going to check the value of 15.85, halfway between them. And what happens if we input 15.85 in as our value of x? Well, we get 4,986.76 ... too low. So it's here, like that. So if you join these up, it would look something like this. Our answer has got to be in between 15.85 and 15.9, which means our value of x is going to round to 15.9 to 1 decimal place. Right, let's have a look at our last example. So the length of a rectangle is 5 centimetres more than its width. Let's sketch our rectangle. Here it is, pink. So the length of the rectangle is 5 centimetres more than the width. I'm going to call the width x, which makes the length x plus 5. Now the area of the rectangle is 90 centimetres squared. Find the length correct to 1 decimal place using trial and improvement. So let's set up our equation. So our equation is x multiplied by x plus 5, length multiplied by width, equals 90. You can expand the brackets here if you want to as well, and we're going to use trial and improvement to find a value of x that satisfies this equation correct to 1 decimal place. If you want to do this yourself and then check your answer afterwards, absolutely fine, otherwise follow it through with the video. So we have x, and then I'm going to expand the brackets, so x squared plus 5x, and let's make sure we have our commentary column here. Remember, our target is 90, so we're comparing how close we are to 90. And I'm going to choose x equals 2 as a starting point, purely because I know 1 is going to be very small. So from here, if we substitute x equals 2 in, we get 14. So let's fill that in here, which of course is too low. So I'll try x equals 3. Let's see what that gives us. So that's 24. That's still too low. So let me try x equals 4. So 36, still too low. Let's try 5. 50, too low. Let's try 6, which is 66, too low. 7. 84, still too low. I definitely regret starting with x equals 2 here. So let's try 8. 104. So that's too high. So I now know that my result must lie somewhere in between 7, which is a bit too low, and 8, which is a little bit too high. So I'm going to try 7.5 next, because we're trying to get our answer down to 1 decimal place. So that's 93.75, which is too high. So I'm going to try 7.4 and see what we get with that. Now that is 91.76, which is also too high. So let's try the next value down, 7.3, and see what that gives us, which is 89.79, which is a little bit too low. So that tells me now that my answer must lie between 7.3 and 7.4. But we want to know, does it round down to 7.3 or up to 7.4? So we're going to test a value in the middle, which is 7.35. Just about got room for this in the table. And that gives me 90.7725, which is slightly high. So looking over here, we know that 7.3 was too low, 7.35 was too high, and 7.4 of course was too high. So we have this, which means the answer would lie in this interval here between 7.3 and 7.35, which means it would round down to 7.3. So that is the value of x. So the length, of course, to 1 decimal place would be 7.3 plus 5, which of course is then 12.3, using trial and improvement accurate to 1 decimal place.